Here's the key for org2test3, and you have the number out of 100. That's your percentage on the test. Then, since it was worth 350 points, that the number that went in the gradebook is there. And then over here on the side is a number, and that's your percentage in class right now, with everything taken into account in the gradebook through right now. So the first one, draw resonance structures. Draw 8 resonance structures. You start where you have the most electron density, send the electrons down. So you get the double bond to the oxygen, a positive charge on it, negative on that atom adjacent to, and then just keep sending the electrons around the ring, 3 atoms at a time, as always. Still have a positive on the oxygen. Now you have 2 double bonds, negative charge, double bond there and that. Send them down, put the negative charge on the atom that has the substituent off of it. Send that down, break the double bond. And that gives us this. And then the last one going out gets the electrons up on the oxygen. So we have a negative on it, a positive on the other oxygen, which I haven't drawn in on all of them. So I'll draw it in, and then just send the electrons back through one step at a time. And then back to the carbon on the ring, negative charge, double bond, positive on the oxygen. And then send it back to the aromatic ring out of where we started. And we get, single bond out to the oxygen, not a double, pardon me. Single bond out to the OME. Then we have a double bond there, double bond on the side chain in the aldehyde. And then the next question, this is cinnamaldehyde, or it can be 1, 2, 3 phenyl, 2 propene, 1L. Then the other nomenclature one is a 1, 2, 3 ethyl cyclohexane carbaldehyde, or carboxaldehyde. Either one would be fine. On the next page we have predict the products, and here we have a reaction that is just like the Wittig. It's actually the Horner-Emmons. So you have a very acidic hydrogen here, you pull it off. If you draw a mechanism, which you will later on in the test, we get to something that looks like that. The alpha beta unsaturated carbon going to the carbonyl of the benzaldehyde we started with. Here we have a regular Wittig. Cinnamaldehyde is just this with the carbonyl there. That's cinnamaldehyde, but when we do a Wittig on it, we lose the carbon-oxygen double bond and replace it with a carbon-carbon double bond, so the product would look like that. In the next one, the first step, we form the enolate with the ethoxide, but when we draw out 1 bromo, 1 cyclohexene, we see that it is sp2 hybridized, and all we're going to do is get our starting material back, and it will not react with that because we can't do an SN2 reaction on the sp2 hybridized carbon. The next one, we have formed the enolate, and then after we form the enolate, which will erase the enolate, we would do the SN2 on benzyl bromide, and remember, benzyl bromide has a CH2 between the bromine and the aromatic ring, so that is what we'd get. And the next one, H- and N-butyllithium do the same thing. I messed up the problem in that I wanted a methyl out here on the end, but it doesn't change what you would do with it. But they're just going to remove the hydrogen here, the very acidic one right here, so we deprotonate that, make the anion, and then have that anion attack the propyl bromide, so we'd end up with this, and then a weak acid H+ would just protonate everything, so the answer would be that. In the next one, we take that answer from before, which looked like this, and when we add hydroxide to it, we raise the OET and we end up with the carboxylate. Then we add acid to that and we'll protonate the OH, and then with the heat we end up decarboxylating that, and we end up losing all of this, so the answer is just the substituted acetophenone. In the next one, we have alpha hydrogen in between the nitrile and the ester, so we're going to remove it. We have benzaldehyde, which everybody remembers, looks like this. And what we're going to end up with is having it go all the way to the alpha beta unsaturated ester, because you only have the aldehyde on there, you don't have an ester on the carbon here, so it stops. It doesn't, it'll end up eliminating your product. In the next one, we have an ester on our leaving group, so what we end up doing is the nucleophile will add into the carbonyl, and the nucleophile is just the base of our ester that has the alpha hydrogen. It'll attack the carbonyl like that, and then after it attacks the carbonyl, we have O- OET and that long bond. We can kick out the OET, reforming our carbonyl, so when we get the carbon oxygen double bond, then we would remove the hydrogen there, and if you had acid, you could either write the negative there or have the hydrogen there, and that would be your correct answer. So if I were to draw it neater than what I did there, which I will, erase all of this and redraw it, we have the carbonyl, and then we have the alpha carbon that looks like that. So that's the answer for that one. In the next one, we form the enamine, which is a single bond to the nitrogen, double bond, 6-membered ring, -5. So we get the enamine, and then the enamine is going to react with the ethyl bromide to do an SN2 displacement, and then we cleave the imine and we get the alpha ethyl compound. On the next one, we see the change going from number 1 to number 2, and all we do is form this bond between the carbon with the oxygen and this vinyl carbon. So what we have to do is take this, make it something that we can add a nucleophile to. We remember from early in the semester, the only way to form a carbon-carbon bond is with a Grignard. Grignards add to ketones, aldehydes, carbonyls, and epoxides. So we need to turn our compound 1 into an aldehyde. So we oxidize it with PCC, and then all we have to do is add the Grignard. And a lot of you are much too creative in what you added. All you need is the vinyl magnesium bromide followed by a dilute acid, and you're done. On the next problem, were the different reactions here shown, and the first one, to make cyclohexanone into that, we could add just ethoxide followed by the ethyl bromide, or we could do LDA followed by the ethyl bromide, or we could do it like the problem on a previous page where we make the enamine and add ethyl bromide. There's a lot of different ways to do it. And the next one, we have to go from the carbonyl to the alpha bromo compound, which is Br2 and H3O plus, and then we can eliminate that with T-butoxide to the alpha beta unsaturated compound, and then with the diethyl cuprate followed by acid, we can Michael in the ethyl group. So the only difference between compounds B and C are, in C we do the one bromine and water, or acid, excuse me, and then 2 the T-butoxide to make the alpha beta unsaturated compound. 3 would be the diethyl cuprate, and then 4 the enolate. Instead of grabbing H plus, we would grab methyl bromide, and that would put the methyl on the alpha carbon, and that would work for C and D. E, we see carbonyl on the alpha carbon, so it is just the nice easy reaction from lab where you add hydroxide, you add benzaldehyde, and you have an excess of the benzaldehyde. You didn't have to write that down, I figured that was in there, and an excess of benzaldehyde, and you get the aldol to happen on both sides of the carbonyl because you have alpha hydrogens on both sides. And in the next one, we have the aldehyde, and just like the problem we worked in class, we have to add it to an alpha beta unsaturated ester. So it would be that, and we'd have ethoxide to pull off the alpha hydrogen, Michael it in, and then you could say to the acid, but if you didn't say that, I didn't take off points for it. And the last one, we want to get a methyl on each side of the carbonyl, so we can do LDA and methyl bromide. That puts 1 on, and to make sure we take off, so here's where we are in number 2 after the second reagent. Not a bromine, methyl. We have this, well, I guess actually after 3, because we did acid after the LDA. So the only way we can pull off this one is we have to use LDA again. If we use ethoxide, methoxide, something like that, we take off the more substituted to form the more stable enolate. So it would be LDA, step 4, step 5, methyl bromide, and step 6, acid. And that gets us there with a methyl on each side. The next question, we have a formula of C9H10O, we have a carbonyl, we have a mono-substituted aromatic ring, we have a doublet and a quartet. The quartet tells us this has to be a hydrogen next to a CH3. This tells us we have to have a CH3 next to a hydrogen. When we measure out the integration, we'll get 1 hydrogen here. This is 5. This is 1 there, and this is 3. So 1, 5, 1, and 3 add up to 10, which is how many hydrogens we have. This signal right here at 10 is for an aldehyde, and then the 5 is a mono-substituted aromatic ring. So we have a mono-substituted aromatic ring, we have a CH, CH3, and we have an aldehyde. And the answer is that. And the next one, N-butyllithium, is a strong base. It pulls off the acidic hydrogen off of our Wittig reagent to draw either resonance structure. This can then go attack the carbonyl. Pardon me, drew too close. Go attack the carbonyl of 3,5-dimethyl cyclohexane carbaldehyde. As it adds to the carbonyl, you got to break the double bond, so that gives us an O-, the ring with the 2 methyls on it, the carbon over here which has 2 methyls on it, the phosphorus which has the 3 phenols and a positive charge. The oxygen adds to it, gives us a POCC ring, 4-membered ring. This carbon has the ring with 2 methyls and a hydrogen off of it. This carbon has 2 methyls and the phosphorus has the 3 phenols. Then for the carbon-oxygen bond, it breaks with the electrons going to oxygen because it's more electronegative, and the carbon-phosphorus bond going to the carbon because it's more electronegative, and that gets us to our product, which unfortunately I had drawn wrong on the test, and it really looks like that with the double bond on the carbon off of the ring, not on the off of the ring itself. And the next question, the extra credit, we have a simple SN2 where the phosphorus has a lone pair. It comes in and attacks the alpha carbon, kicking out the bromine, which gives us this with a positive charge on the phosphorus, and then the bromine comes in, does another SN2, kicks it out, and bam, we're done. Then here, as I alluded to earlier in the mechanism, we pull off the acidic hydrogen to get to the phosphorus with the double bond and negative charge. That hydrogen is very acidic because it's in between the phosphorus and oxygen double bond and the carbonyl on the other side. Once we form that, it can add to the carbonyl, breaking the carbon-oxygen double bond, so we end up with a phosphorus with 2 double bond oxygen, 2 OETs, bond down to carbon, methyl, carbonyl, I just added a carbon. That this carbon is connected to the carbon that has the oxygen on it, hydrogen and a phenyl. This oxygen can form the 4-membered ring, POCC, H in phenyl, ATO2, O minus. The carbon oxygen double bond breaks towards phenyl, carbon phosphorus double bond breaks towards carbon, and we end up with our products. And this question here is one very similar to what we did in class. This is out of the next section of the class, actually. And just like in the section we were in on ketones and aldehydes, we protonate our carbonyl first, then methanol adds in, to get there, and then we have to remove the extra hydrogen, and methanol will come in and grab it, give us the neutral molecule again, and then we protonate one of our OHs from an acidic methanol to give us this with the really good leaving group on it. Now that it has a positive charge, we can kick it out, and we have the protonated carbonyl with the oxygen, the ester off of it, and then a water or a methanol, it doesn't matter which one. You got a bunch of each around, could come in and grab it off to give us our product. And there's the key for the test. Look it over, see what you missed, come in and ask about it anytime, and we can talk about it later. Thank you.